slides there, Maarten?
Yeah, can.
Okay, all right. So the topic of today's webinar is seismic stratigraphy, depositional sequences, presented by Maarten Weimer. Maarten's an exploration geologist. I'll let him do a brief intro to himself. As I mentioned, I'm the director of SANDA, Upstream Oil and Gas Training Specialists. So if you're interested in any training or any learning and development requirements, capability assessments, we're the people to talk to. We've got, this is part of a series of webinars that we've been running since December last year and been very successful. And as I mentioned, this one's being run by Maarten. We've got ESG risk management coming up, minimum safe abandonment pressure decommissioning in July, subsea umbilicals, rises and flow lines. If you're interested in that, it might be a topic that a lot of subsurface people aren't familiar with. And the role of sealing on the distribution of trapped oil and gas, very technical one there, and gas well performance to finish off the year. We might have one more in December. We haven't decided on the topic there yet, but that will wrap up the year for us. As I said, they've been very successful webinars, and we'd like to see you at all of them if you're interested. If you're interested in the training side of things or want to inquire about what we can do for you, we can organise a meeting. You can take a photo of that QR code and arrange a meeting, or just through the link there, and that will arrange a meeting with myself to discuss your training needs and or what else we might be able to do for your organisation. Finally, we'll mute all attendees, and as I mentioned, you can use the chat function. I'll try and answer any questions I can during the sessions, but anything that's beyond my technical capabilities, as I'm not a subsurface person, we'll hand over to Maarten at the end of the session. If we don't address all the questions live, which we should be able to do, we'll follow up by email. And if anyone has any questions after the webinar, sorry, you can send an email and we'll follow up on that. We're recording the webinar, so you can access it again on YouTube if you want, or share with your colleagues or friends. And as mentioned, any further questions, just contact us at training@sandaengineering.com. Okay. Now I'll hand over to Maarten, and he can introduce himself and carry out the webinar. Okay. Thanks, Maarten.
Okay. Let me just share my screen. So you can see the screen?
Yep, got it. Great.
Okay, very good. Okay, thanks Anastasis for organizing the webinar. So the next 40 minutes or so, I will take you through, say, some of the basic concepts of seismic stratigraphy, and the full title is Seismic Stratigraphy, Depositional Sequences and Systems Tracts. And that is not just a standalone thing, and at least in my mind, is always linked to gaining knowledge on reservoir distribution and reservoir delineation. So that in principle is the subject we want to talk about this morning. About myself, Anastasis already said I'm an exploration geologist. That's absolutely true. So I have an exploration background, worked for Shell, both I'm based in Holland now, in the Netherlands, but worked for Shell most of the larger part of my career abroad, but also back in Holland in the Shell Research Center, did geology research, and also had a stint in training, and also worked in new ventures. So fairly, from a company point of view, fairly broad spectrum. My background, though, is really exploration geologist, and say my discipline route is very much in reservoir geology and seismic stratigraphy. I'll just go and show you basically the start of my career. That was in Oman, and I like this this picture because it shows the Oman Mountains, and we actually did field geology in the Oman Mountains, and it is of interest because if you go further to the south across the Oman Mountains, then you go to the Oman subsurface. You have a major oil and gas province. Many of the rocks in the subsurface there outcrop in the Oman Mountains, and it is one of these places where outcrops have a direct link to what we see in the subsurface. And to me, most of us we were spending a lot of time in front of the workstation or in front of the computer screen, looking at digital data. And every now and then, it is really a must, in my view, for geoscientists to go back and to look at rocks in real life, touch them, discuss them, just to calibrate your technical mindset, so to speak. So in Oman, that was a beautiful way to actually start to link outcrop observations with the subsurface. Now these days, since I'm retired from Shell, I do still, I'm an independent, as they call it, independent consultant and trainer. So I do both training work, mostly in the realm of seismic stratigraphy, but also play-based evaluation, risk of exploration, risk of volumetrics. My main interest is in reservoir delineation and seismic via the seismic stratigraphy route, so to speak. Consultancy I like, and the picture shows a portfolio, an exploration portfolio review we did in Suriname, which is recently has joined the countries which have significant oil reserves. And this to me, this picture shows the informal nature and the discussion element you have, you should have in consultancies, but you also should have in training. So one of the things I find interesting about training, which energizes training, is if you have an open discussion during the actual training period. Now in this case, it's 40 minutes one way, and then you have chance to actually have the discussion and ask questions. But that is the mode we're in at the moment. I just wanted to illustrate this this picture that discussion is one of those key ways to actually learn rather than just listen. Anyway, enough about that. Let's start our technical webinar. And looking at this this photograph, I found it in a Dutch newspaper paper a couple of weeks ago. It's a famous photographer who made this picture. And you can of course wonder why it is so interesting, and what is the relation with seismic stratigraphy. I tell you. So just I have here and there some text blocks also to you can read while I'm talking. And one of the elements in exploration, the key element is understanding the potential distribution of reservoir seal and source rocks. And as I mentioned, I'm particularly interested in the reservoir aspect, but of course seal, source rocks and trap are of equal importance. And even if you move to exploration and understand this myself, we had a discussion. If you move from exploration towards appraisal development, of course, the geological element of our business still plays a major role, and it is often an interesting place to be as a geologist because you interface with what are the engineers, what are the technical people actually doing with your data. So it's an interesting place to be. And seismic stratigraphy still plays a role even in those more detailed reservoir evaluation environments we're in once we are in a moving towards appraisal and development. Now for this webinar, we're really focusing on seismic stratigraphy. And seismic stratigraphy is interesting, and it's different from, say, conventional seismic interpretation, because rather than looking at specific markers, horizons, map, find the structural geometries, seismic stratigraphy more looks at packages of seismic reflections, especially the geometries which represent stratigraphic geometries. Seismic stratigraphy also looks at, let's say, seismic facies patterns and how can I translate those to geological facies patterns. So seismic stratigraphy is more a pattern recognition type of approach towards our seismic data set. So pattern recognition is important, but equally important is the calibration of those patterns on seismic with geological data. So seismic stratigraphy really you should not just stay with the seismic patterns you see. You should also link that with whatever log data you have or whatever analog analog outcrop data you have. So it's also a discipline which should integrate geological data. Now, why this picture? If you look at this, it's an interesting one. If you don't know what you're looking for, it's actually difficult to actually see this animal, this snow leopard sitting there in the center. So to me, it's an interesting one, because if you really don't know that animal is there, it's actually not easy to spot. And with seismic stratigraphy, it's a bit the same. If you have no clue about stratigraphic geometries, about what sedimentary depositional facies, what sort of patterns they have, then it's not so easy to actually distill that from a seismic data set. So knowledge about geological patterns is very useful to actually recognize these patterns on the seismic. Okay, now just to illustrate it a bit, this is just a seismic line segment, and I took that from the APG Explorer. I like the APG Explorer because often it has interesting articles, but especially it has interesting seismic lines or seismic segments which are part of the advertisements, and they're a good source for examples, so to speak. Now this one I took out. It comes from the Mexican side, from the Gulf of Mexico, close to the Yucatan Peninsula, as you see in the lower right, lower left map. And it just shows a number of features. And just to familiarize ourselves a bit with the type of observation we want to make, we'll go through this line segment. And for those who straight away say, but what is the scale? There's actually no scale on this this section as it was in the APG Explorer. So we have to live with just the image as it is. So if we look at this one, I guess you can't be surprised that we start to look at this anticlinal feature, this amplitude pattern. So here you see bright amplitude, and although the reflection continues, the amplitude changes. We also see patterns here which seem to be cross-cutting the anticlinal shape here, so they're more flattish. I guess most of you will start to recognize what that potentially can mean. Other patterns you see a bit vague in this line are these cross-cutting reflection patterns. These are essentially what we call geophysical noise, acquisition noise. You see more of these cross-cutting trends. So here also a seismic stratigrapher, he needs to be relatively close to the seismic processor to check, hey, is this something geological, or is this something to do with acquisition or processing of the seismic data? When you go deeper, we see actually that although we still have that anticlinal shape, we see that what we call the frequency, so how spiked are the reflections, starts to decrease. There's often a pattern we see that this is not necessarily a facies issue. This is something inherent to seismic data, that you have less energy in the deeper subsurface. So the frequency of the seismic data starts to decrease. So this is something you should normally see in seismic data. So I already give it away. I'm too quick here. If we see these patterns, the anticlinal shape, but here we see a set of reflections that seem to have a steeper dip than the underlying and the overlying. They're not like these cross-cutting events where you see these reflections, you follow it, start to peel up, have a steeper dip, and then abuts against this underlying reflection. This essentially is stratigraphic data. This is a stratigraphic geometry. This is actually, these are delta shapes. These are the shape, the reflection shape linked to a prograding delta. So this is a nice example of the type of geometries we try to obtain from the seismic data. If we go further up, we see this surface quite marked, which seems to be truncating underlying reflection. So this is an important stratigraphic surface, and actually an erosional surface, a unconformity for all intents and purposes, which is nicely expressed on this seismic line. Of course, we're only looking at the relatively small window. So is this an unconformity just linked to truncation of this anticlinal feature, or is a more regional unconformity? For that, we would have to zoom out and see more of the seismic. But further up, we see these wavy and down-cutting, small-scale down-cutting features. And this is typically for deep water channelized type of deposit. So without blinking, I can straight away tell you that this is likely deep water, because the scale of channel EV systems of erosional features is typically for the deep water, and you would not easily see that onshore. I'm always also supported by that by looking just here in the upper right corner. I see this large scale wavy nature of the reflections. This is fairly typical for what we call deep water contourite. So that also supports the interpretation that here I'm looking at reflection geometries linked to a deep water setting. So without knowing much about the background, just looking at this seismic line, looking at the reflection patterns and the reflection geometries, I can already see gain quite a lot of information, stratigraphic information, on what sort of subsurface sequence am I actually looking at. Now, this is the type of observations I want to take you through, and I want to take you through how we can systematize that a bit and put that into a seismic stratigraphic model. This line. Okay, let's just take one step back and just look at the schematic drawing of a basin margin, basin fill, and just look quickly at the what are the overall controls on the nature of the basin fill. And obviously it's what is happening to the sea level. What if the sea level would go up, you create more accommodation space. If the sea level goes down, create less accommodation space. On the other hand, you have tectonic processes which would uplift the basin floor or accelerate subsidence. So those two together roughly dominate the amount of accommodation space you actually have in the basin, which you want to fill with sediments. I just mentioned that subsidence uplift, so tectonic processes. Then, of course, the other major control is sediment supply. So how much sediment do I actually push in my basin, into my basin? And again, these are related to the type of hinterland, the tectonic processes, climatic processes. So they're all sort of secondary elements which govern sediment supply. Sediment transport dynamics. What do we mean with that? It's basically how much do these rivers switch. This is a delta lobe. Do I build out here, but then the lobe switches. So it's sediment transport dynamics. How much longshore currents do I have? What is the wave action, etc., etc. What is how easy is it to actually distribute sediment along the margin? Those are secondary but important dynamics to my basin fill pattern. Slope stability is an issue. Carbonate productivity, if you have basically the environment where you can produce carbonates. How much carbonates do I produce? What is their shape? How do they bail out? All these are of importance to my basin fill nature. And the last one I want to mention is basically the topography of my basin and what is the symmetry of the basin. You can imagine that the depositional patterns will vary if this is a very low inclined basin slope or if there's a much more steeper slope. So the geometry, the topography of the basin is also an element which plays a significant role. So in a nutshell, these are the sort of factors which control my basin fill, and hence they control the depositional systems and the depositional geometries of my basin fill. Good. I'll take you a bit back to this idea of basin margin geometry, stratigraphic geometries, because it looks like a bit these days that seismic and sequence stratigraphy, when that came up, at the moment we started to talk about basin fill geometries, the stratigraphic geometries, that basin fills have a certain topography during the deposition. But earlier, we already have literature, and this is one from comes from the Midland Basin in Texas, this diagram. Maybe I'll just check with you here. This cross section is actually not based on seismic. This is based on just electrical log analysis. And maybe it's also good to look at the scale. So scale, vertical scale bar at 400 meters, horizontal scale bar is 7 kilometers. So that means you have a strong vertical exaggeration in the order of 16 times. So in reality, of course, the dips are less steep than they are on this drawing. So we have an overall structural dip in the order of, say, 1 degree. And then the depositional dips are up to 4 degrees. So you have to bear that in mind, that actually the dips are much lower than indicated on this diagram. Nonetheless, this say, electrical log-based diagram shows regional stratigraphic geometry. It shows the relatively, say, the shell top, the relatively shallow, and it shows a depositional dip. Then it's soling out towards the base of the basin. So we see these type of S shapes, and that all was done by one of the people who was doing this was Mr. Jackson, who published this in 1964. Already in those days, people had the idea that stratigraphy is not all layer cake. We have a morphology, a stratigraphic topography, a basin margin, progradational geometry, which governs our basin fills. Now, I have to take you a few definitions, not too many, so don't worry about that. But this is the classical one of the depositional sequences. So the lines, see the green lines, basically they already indicate the same type of, say, S shapes I just showed you in the previous pattern. Scale can be from tens to hundreds of kilometers. Vertical scales also vary. It's really the geometry which is of importance. And the classical definition now of a depositional sequence, which derives from the famous AAPG memoir 26 by the Mitchum and his co-workers in Exxon, and of course the name Vail is the name which the person, the geologist who was part of that group, and he came for the first time with the global sea level curve. Now that's not going to be the subject for today, but depositional sequences are. So the depositional sequence is a stratigraphic sequence bounded by subaerial unconformities or their correlative conformities. Subaerial conformities very much in the inboard, and then if you would trace that uniformity basinwards, that stratigraphic surface grades into a conformity. So that's why the word correlative conformity is in there. And originally, the depositional sequence is basically the stratigraphic entity which is contained between those two subaerial uniformities and their correlative conformity. So that the definition of depositional sequence is that it's bound by two uniformities. Now, often this or more recent days, people add that the depositional sequence is a relatively conformable succession of genetically related strata. So that means what you have actually sitting here in between the two depositional sequence boundaries, essentially we have no major, no unconformities, no major stratigraphic disruptions sitting in the depositional sequence. It's for all intents and purposes, it's a coherent stratigraphic unit. Now, sometimes you have very local, say, unconformities there, but no major regional unconformities should be sitting in between the two sequence boundaries. Then the second term here, genetically related strata, essentially wants to say that from a depositional systems point of view, the sediments deposited here in the depositional sequence, they talk to each other, they are linked. And that is the step we're going to make from that genetically related strata, that linkage towards the idea of systems tracts. And we're going to go back to that idea of systems tracts, basically governing the actual nature of sediment distribution, sedimentary facies within the depositional sequence. Now, to start by just the illustration of a depositional sequence boundary, in this case we start in the field. This is a coastal section in northwest Borneo, offshore on the coast of Sarawak, Miri, where I spent a number of years and spent a lot of my weekend time and just looking at these nice outcrops. You see a structural dip here. This is structural in the order of 30 degrees or so. And then towards the top, we see this sharp surface, and I could have a couple of meters of sediment sitting on top, which are more or less horizontally bedded. Now, this surface essentially here is a erosional unconformity. Cliff height is in the order of 15 to 20 meters structural dip, and with the green line I've indicated this truncation surface. In seismic stratigraphy, actually, we often use, and it depends a bit which company you're from, but then I at least Shell taught me to use green for the uniformity surface and use red arrows to indicate the truncated reflection, the truncated beds which define the uniformity surface. So that's basically what I use these colors, but that's not a global convention. The idea of using reflection terminations to define the surface is an important one. Okay, if you go a bit more inland, so if you walk from here a bit inland, you see more outcrops, and these dipping layers are exactly the same as we see here in the cross section. You can still see the conformity surface here with the horizontal bedded sediments on top. So essentially, it's the same surface as we looked at in the headland. Now, in that on that surface, the sediments here, they are coastal. They're a bay type of sediments, sandy. Here and there some clay, but here and there you also still find mangrove remnants of mangrove trunks here in the sediment. So that's quite neat to actually have just a couple of 100 meters beyond the headland, the present day mangrove trees sitting there on the muddy and sandy coastal beaches or embayments. And here we have Pleistocene, so quaternary sediments which contain fossil remnants of the mangrove trees. So those two photographs, if I now evoke a seismic line which is taken in the offshore of North Sarawak, we're looking now at, say, if you would place the photographs just here towards the left, then this surface here is basically the same surface as we see here on land. So it's actually quite nice that you're quite nearly a direct link between your onshore outcrop observations and the offshore seismic. So if I put some color on that seismic line, this is that conformity surface. And I think I've indicated maybe even an older surface. That older surface is basically truncated by the younger conformity. Now, the interesting element here to see is that if you go here in the inboard, you see very much the same pattern as we see here. If you're going more outboard, you see that the angular conformity element starts to disappear. Only where I still deformation linked to fault movement, I still have this truncation, but as soon as I go into the broad, gentle synclinal areas, I'm nearly getting into the conformable phase. So for all intents and purposes, I'm looking here at a sequence boundary. And if I would go further offshore, slowly we start to become more and more conformable. So this is to me a nice example of a depositional sequence boundary. If I would have the same argument for this one, then in between I would have my depositional sequence. Now the element which makes this let's say separate from the classical idea of depositional sequence boundaries and depositional sequences is that in this case it's structural deformation which actually causes the conformity. So it's not, say, sea level drop. It's in this case structural deformation which governs the depositional sequence boundaries and patterns. And that is something I want to bring forward in this talk, that we can, in my view, only a few areas on this world, it is the relative sea level curve which dominates the depositional sequence formation and geometries. But in many areas in the world, we have active structure deformation. Structure deformation plays a key role in the definition of my sequence boundaries and my depositional sequence geometry. So I think that is an important point to take away from this little example. Okay, I think let's move on. Now, I can't step away from this area and not showing you the present day situation. So we actually looked at the headland here from the other side. I've walked through a bit. Here I still see the truncated surface, the present day truncated surface of these inclined beds. So we're still looking at the dip. It's a little bit steeper here, 35, 40 degrees. And here we have the waves cutting into the cliff and creating this flat surface. So essentially, I'm creating a sequence boundary here. So this is a sequence boundary, a later one than the one we looked at before. So this is the present day erosional surface eating into the coastline and basically forming the sequence boundary in the making. And of course, I took this picture because on top of that sequence boundary, we already see some deposition, in this case, of beach sands. So the next depositional sequence sitting on top of this sequence boundary is also starting to be formed. So that is, to me, is interesting to demonstrate that if we talk about depositional sequences and depositional sequence boundaries, often in real life, you can actually see these processes, that they are actually active, and that this whole idea of sequence boundaries and depositional sequences makes sense. So in the diagram, you see the what I was basically discussing. This is the surface we're looking at here. This is the coastal cliff, which is retreating. While it is being formed and while it is retreating, we get the beach sediments covering the uniformity and basically moving inboard together with the erosion. Now that means that this surface is actually has is diachronous, is time transgressive. So let's leave that that subject of sequence boundaries for the moment. In seismic stratigraphy, but also in sequence stratigraphy, in sedimentology, we often use the terms regression and transgression. So just to clarify what we mean with regression and transgression, of this simple diagram, I have a coastline, a profile here. This is the coast, this is the sea level, landward towards the left, seawards towards the right. Now, if the coastline, for whatever reason, moves seaward, moves basinwards, we are in a regression mode. This is regression. Simply what the word regression means in this context. Now we can go the other way. If the coastline moves inward, moves landward, then we are in transgression. So there are lots of terms. Geologists are good in terminology, using more words for the same thing. But in building, or it's the same as transgression. You're moving the coastline inland, inboard. Now, with regression, actually you have two types of regression. You have if the relative sea level, either due to uplift or to global sea level drop, doesn't matter. If the accommodation space decreases, it means that your system is forced to move basinward. So your coastline has no choice; it has to move out basinward. That's what when we talk about a forced regression. So in this case, if the coastline just moves out and it has no choice. You also have a case where I'm actually in a mode where my accommodation space, my relative sea level, still increases. But if I have enough sediment to put in that increased accommodation space, I can still build out my depositional system, and my coastline will still move out. Although I'm in a mode that I'm creating accommodation space, or my relative sea level increases. If I have enough sediment, I can just cope with that and actually build out and fill the accommodation space. And this is what we call normal regression. So I make this point that with transgression, it's simple, but with regression, we actually have two types of regression: forced and normal. Okay. Now, we talked about sequence boundaries. What is in between the sequence boundaries is the depositional sequence. And we talked about transgression and regression basically moves out, the moving out of the shoreline, or the moving inboard of the shoreline. Now here, I would like to start talking about what is actually the nature of the depositional of the sediments, what is their stratigraphic organization within the depositional sequence. And for that, I've taken this as example of just again the coast. I have a pool of water here, and actually I see a sort of mini river system, sediment supply here, the river here, mini river. It's like a flume experiment, flume tank experiment. And here it's building out what we would call, for all intents and purposes, a little delta. So this is the setting. Now, I just want to illustrate to you what is happening if this level of the pool, the water level, actually rises or drops. What is happening to this system? So I'm going to show you a diagram along this trajectory. So this is the situation as we observe now. So essentially here we're looking at an erosional surface. Supply comes from here. Then here is the level of the pool. Is for those with the observant ones among you see that there is a sort of S shape here. The upper part of that S, the sloping part, and then that shows out. And that's basically this the morphology, the topography of this deltaic system. So flat, shallow here, then the slope and the base of slope. Now, if I would still have sediment being transported to this system and the water level remains as it is, I would be building out. The delta would be growing and starting to fill this water basin. So in this case, the delta just pushes out and fills the remaining water basin here, the accommodation space, with sediment. What happens now if I'm increasing if I'm upping my water level, my relative sea level? So this creating accommodation space. So now I have created accommodation space by increasing my sea level. If I have enough sediment actually being pushed along the system into the basin, I first need to fill the accommodation space here in the flat upper part. Then still, if I have enough, I can prograde out. So here I would create a prograding delta system which builds up and progrades out. Now what happens if actually I go, in this case, we would have a normal regression as indicated. Now what happens if I actually dropping my water level? In that case, I would have erosion. Basically, I'm eroding into the flat upper part, and sediment is being pushed out into the basin and have no building. I go back into basically a eroded delta top and sediment still being pushed out into that little basin. So for all intents and purposes, what I'm doing by that lowering of the water level, having a forced regression, creating an erosional surface here. So essentially, I create a depositional sequence boundary here, and where I still am here at the slope and base of slope, I have continuous deposition. So this is just an example of what we mean with the depositional sequence boundary. Now, if we move on to a seismic line, this is a seismic line from the North Sea, what we call the Eridanos Delta example. You see these sigmoid shapes, and in the regional seismic, you always have to be careful that we are in a squeezed mode, so the dips are exaggerated, as we saw on this early example of a basin margin of Midland Basin in Texas. Here we see these sigmoids, we see these S shapes. And observations to make are that there's a lot of internal variation in these shapes. All these S shapes, the basis of these S shapes, basically flattening out on a similar surface. Towards the top, you see that it jumps a bit. There are variations here, but overall, you see here this S shape. Here you see that the S shape is truncated. You see it truncated, and here it's building up again. So there's a variation in the upper surface. Either it's these upper flat units are being deposited, or they are not being deposited or even eroded. But the basal part is all these S shapes. They amalgamate at the basal surface. Now I'll put some colors on the seismic line. You see I use the red arrows defining this inconformity surface. So I'm actually looking at this surface here. So do I see more of these erosional surfaces? I see one there. And you can, the yellow is just to indicate this rather strange unit in between. We can ignore it in the overall pattern, but basically have slope instability. So I have the onset of a slide or a slump here, but that is secondary type of observation. At first, want to look at the overall S-shaped pattern, and the name for those S-shapes is actually, again, we have more terms for those S-shapes: sigmoidal patterns or clinoforms. Clinoforms is maybe the term used as the most general distribution. We are a horrible people in nomenclature, I'm afraid. So by putting colors on these patterns, we can try to analyze these stratigraphic packages. So first, the erosional surfaces, the sequence boundaries, and then we're going to look at this lower surface where all these basically these S shapes where they amalgamate. I've indicated here two DSs, so two depositional sequences, because if we keep on using the definition that they are bound by sequence boundaries, this would be a sequence boundary, this would be a sequence, and this would be a sequence where the actual underlying sequence boundary is not visible. Now, what is actually happening here? We see that the upper part of the sigmoids are truncated, while with the next sequence boundaries, we see that we actually have an upbuilding of the sequence and then a building out. So this is how we can start to analyze these type of sections in terms of the positional sequence boundaries and the positional sequences. Before we go there, I think I haven't mentioned these names. Maybe you're familiar with those. If we're looking at these clinoforms, these S shapes, then the upper part we call top set, the sloping part we call foreset, and the bottom part, that's flattening out, we call bottom set. So these are terms you often see, and together they form the clinoform geometry. Now, this picture I saw the other day again in the APG Explorer. It shows a outcrop, actually not on this Earth, but on Mars. It shows the image in the Jericho creator where the Mars rover is slowly creeping around and taking images. And it's so fascinating that you see, as they say, bottom sets, foresets, and top sets. You see the inclined surfaces. This interval is in the order of 10 meters thick, so it's the seismic line we looked at just now, of course, is an order of magnitude larger than this outcrop, but essentially we still see the same stratigraphic geometries. So it looks like that seismic stratigraphy is not limited to Earth, but we can actually export it to our Mars observations. And in this case, the foresets are all, you see that the surfaces are actually of the top of the foresets are truncated. So these what they call top sets are actually not linked to these foresets. They're a later phase. And this type of pattern is what we call a Hilbert delta type of delta, or a Venn delta type of delta. So not directly comparable to the previous Eridanus delta. So quite interesting that these geometries are just not just linked to Earth situations; they are universal, so to speak. Now let's not dwell on that too much. Because of different gravity, etc., the dips in this case of the foreset are quite steep. That's also quite characteristic for these Gilbert or Venn delta types. Okay, let's move on. What I think we need to do is now go into the depositional sequence and look at the what we call the systems tract. What are the depositional systems we actually fill the depositional sequence? And But I've indicated here a number of these sigmoids, and now I'm linking that to what we call the relative sea level curve. And the relative sea level curve has in it the amalgamation of what is happening to the accommodation space. So it's global sea level change merged with subsidence or uplift, which creates then the relative sea level curve. So let's first start. This we know now. We have top sets, forward bottom sets. Now we're actually dropping our relative sea level curve. That means we're starting to erode into our top sets, and we maybe deposit some sediments here at the base of the slope of our forward sets. So this is the formation of the sequence boundary. And we have the forced regression, as we discussed. Now, what's going to happen here? The drop fades out, and we're going into slow increase. And we start to recuperate. We start to build up and create small clinoforms here, starting to build in. This part is often still what we call this part together is what we call the Lowstand system tract. The Lowstand system tract. Now, if we're starting to accelerate our relative sea level rise, we create our transgressive system tract because we start to rapidly build in. We're basically drowning our sequence boundary. That is called the transgressive system tract. Then we still are in a mode of relative sea level rise. The sediment supply system recuperates from that transgression, and we're starting to build out again. We're building up and we build out. Now the boundary between this phase where we're building up and out again and the transgressive system tract is called the maximum flooding surface. And that is the surface where the coastline is most inboard. Then the system picks up again and we're starting to build up and build out. So we go here into normal regression mode. So normal regression in the high stand and forced regression in the low stand. So low stand, transgressive system tract, high stand system tract. Those are the basic system tracts filling our depositional sequences. And on the seismic line, basically we see the same pattern. This, by the way, is called the axon slug. Apparently people see a slug shape into this, and that is the nickname for it. So here we see I guess you recognize the patterns now. You see the four sets are always good to pick out. The four sets here are top sets, bottom sets here. Here at the base, though, we see something happening, and I'll take you through I'll put some colors on this. You see that we know that we are inland here, basinwards there, and we see that we are actually pinching out on top of this blue surface. And so we're building out, and this would be the amalgamation surface as we saw in the previous line in the North Sea. Another one. Here we see some arrows, some truncations. Here we see truncation. There we have a green line, basically sequence boundary. Then we're moving back to a flooding surface. Orange lines are some let's say support lines. Truncations here, sequence boundary. Another major sequence boundary, all linked to this salt dome here, and then a long phase of just upbuilding and progression. So this whole sequence basically is one high stand sequence. And so the secondary scale, you have some in-building phases of that high stand system tract, but you see this one continuous sick depositional sequence. So in this manner, by using the idea of depositional sequences, using the red arrows and the green lines for indicating the sequence boundaries, coloring in four sets, we can start to analyze the geometry and stratigraphic history of such a basin fill. Now, in view of time, I think I'll leave this diagram as it is. It basically just depicts what is happening with variation between the speed, the rate of relative sea level rise and the rate of sediment supply, which governs this jigsaw type of pattern. So here you could imagine that either you have an increase of relative sea level rise or a decrease of our sediment supply. So we have a short building in phase, building out again, where it builds up. That is basically governed by the rate of sediment supply versus the rate of relative sea level change. I'll just bring you to Spain, where we're looking at the line of the Ebro Delta in the Western Mediterranean. And the typical approach from a seismic stratigraphy point of view would be to look at such a line, and just before you straight away you zoom in and start to put in lines. And if you look at such a line, you actually see the big packages you can actually see appearing. There's a chaotic one here, with this sharp surface here, and somewhere here I see truncations, then a package another level with truncations. So you can already see that I'm looking at maybe at 3 or 4 depositional sequences. When I put the arrows there, then I can put the sequence boundaries. And the challenge, of course, is that it's such a line, you have an endless series of reflection terminations, but these reflection terminations need to actually form a conformity surface. Now then I put in blue the four-setted parts, because that gives character. I can distinguish the top sets from the bottom sets. And it's interesting to see that here they're well defined, or here they are say, much more wispy. The bottom sets, and the fact that the nature of these four sets are different, more wispy here, actually has to do with am I actually looking at the proper positional cross section, or am I looking at what we call a tangential section? So if I'm much closer to my cross section, the trajectory of my seismic line, I'm nearing the direction of propagation of the delta, then I would see a false, much lower dip. Well, here I'm probably more in the propagational direction, and I see the steeper dip. So you always have essentially you have to think in 3 dimensions to analyze that. The top sets, and here a earlier unit, which is maybe as the first infill of this topography. Then on the conformity loop here, I have this big white loop, and I have a downlap on top of the purple loop. So this is how I can start to analyze, before I know anything of this area, what are the deposition, what is the stratigraphic history, what are the deposition, what is the nature of the stratigraphic geometries, what are the boundaries, what type of facies can I expect. And interestingly, I believe that these units open, of course they should be colored in, because these are my Lowstand deposits, Lowstand system deposits linked to these inconformities. You see that these have no four sets, top sets, and basically base of slope type deposits. And of course, these are interesting, but maybe I have sandy deposits here linked to the erosion of the top sets. Then they're covered by shaly bottom sets and potentially give me a stratigraphic tropic trapping geometry. So these are the type of so how you build up your information about the positional systems in such basin fills. In this case, I actually have a field on the line, and that field actually sits here just on top. We're looking at a carbonate landscape, a rift sequence. The carbonates are tilted blocks. They're castified. They got drowned, and then on top of the horse blocks, you still have the second phase of carbonate formation, which is these purple units before they got covered by the distal part of the Ebro Delta. And this system, basically, these four sets and bottom sets form the seal for the reservoir here, calcified reservoir in the subsurface. And this is typical image of the Casablanca field, one of the few producing oil fields in the past of the Spanish offshore. Okay, I think I don't want to rush through this one. This is now a completely different part of the world. This is Northwest Borneo again, and we're looking at the Brunei Sabah margin. And what I want to illustrate here is that you have two structural provinces. We have the province here of the region of Gross Fault, the counter regional. We have four centered units filling the depocenter related to the Gross Fault, and then we go further down the basin. We're getting into deeper water, and you see the typical channel V complexes of the deep water. Now, the point to make is actually that most of the sand in this system and along this trajectory is captured by the Gross Fault. So in this depocenter, little of the topset sand actually gets across this counter regional. Here, though, I see these channel V complexes, and I'm pretty sure that sand sits in these levees and in these channel fills. Now, in this case, that means the sand didn't straight away come from the inboard, but comes along the margin of this system. So it has a different input point, and these two systems are, from a depositional system point of view, not directly linked. Now, I think I'm running out of time, so I'm just taking you to this this last slide, and just want to give you the example of four very schematic wells, and the yellow is reservoir, and blue is basically non-reservoir. Now, the question is how I'm going to correlate the sands between these wells. Now, there are many ways of doing this. One way is, if you're extremely conservative, you don't link up any of the sands. If you're a bit less conservative, you start linking up some of the sands. And the yellow blobs here, the images you see, basically adhere to the data. Now, this starts to link up more and more of the sands. Maybe not extremely realistic, but that's the way you can still do it. You adhere to the data. Now, this is extremely optimistic, still adheres to the information you have. No, this is over the top. It still adheres to the data we have. And this actually is maybe even more over the top, but still adheres to the data we have. And the morale of this story is that in looking at our reservoir delineations, looking at our seismic, looking at our logs, we still have to build a coherent geological concept to actually guide us for interpreting between, say, data sets to come to a reservoir distribution model. So we can't just let go and say, okay, we put this all into our computer and see what comes out. We need to guide these type of reservoir delineations by a coherent, good conceptual geological model. And seismic stratigraphy is typically a method where we try to look at the stratigraphic geometries, at the stratigraphic patterns, at the reflection patterns, and distill a distribution model of our sediments, which is coherent and which can lead to a good reservoir distribution model. So with that, I think I'll close and hand back to Anastasia.